Hello, everyone. I'm Sina Baharlouei, and today I'm going to present a stochastic framework for fair learning in the presence of the distribution shift. And this is a joint work with my advisor, Mason. So as you know, many machine learning algorithms can be biased against women or racial minorities, and many different algorithms are developed to mitigate fairness in machine learning problems. However, a common assumption of them is that the training and test data have the same distribution. And the training samples are IID samples from the target domain or test data. However, it's not always the case. It's not always true. For example, in healthcare, it is possible that you learn a fair model in a hospital A. When you transfer it to another hospital, it is not fair anymore. Or let's say you want to predict credit score of people independent of their race. In California, you learn a model, it is fair in California. When you transfer it to another domain, let's say another state, Texas, you can see it is not fair anymore. And this is a problem we face in many different fairness problems. And the main tool we have for handling this kind of distribution shifts is distributionally robust optimization. And here we have a formulation where the first term is like regular accuracy term in all machine learning problems. The second term is for fairness, somehow measuring the independence of our predictions and that protected group. So we want to do prediction independent of the gender or race. And this lambda shows how much we want to put weight on the fairness. And that maximization problem is for taking care of the distribution shift. We assume that the data, the test data is not exactly like the training data. It is within an uncertainty set around the distribution of the training. And here we have three criteria for finding this, for basically choosing the independence measure and the uncertainty set. One is it should capture complicated correlations. Just linear correlation is not enough to capture all types of dependence between like sensitive attributes and our predictions. Second, we need to have a tractable formulation, meaning that it should be solvable from a mathematical perspective, from an optimization perspective. And last, it should be scalable, meaning we should be able to use stochastic algorithms, like using small batches of data for updating. So in this problem, we use exponential random mutual information as a measure of fairness violation, and LP norm balls as the uncertainty set. And yeah, so there are two take-home messages. One is by choosing them, we can find a tractable formulation, a tractable min-max problem. The maximization problem is strongly concave, and we can use the standard first-order algorithms to show convergence to optimal for both full batch setting and randomized stochastic setting. Moreover, we can show that by proper choice of the hyperparameters, like epsilon for the size of the distribution shift and lambda for the amount of weight we want to put on fairness, we can guarantee we have fairness on the test domain. For example, we can minimize the demographic parity as much as the problem desires. And here I just show one result. There is a data set, new adult data set. Here, there are 50 states, and the task is to predict whether people are high income or low income, independent of their gender. We don't want to be biased against women. And So here we choose one state as the in-distribution data. We train on that data set, and then we transfer it to other states to see how does it work in other states. And the gray one is our approach. So the y-axis is accuracy, and the x-axis is the fairness part. And for this nearly the same amount of accuracy compared to others, we reach to better fairness and more robust fairness, less fluctuation in fairness. Thank you.